Hi everyone, welcome to the Learning Connection today. My name is Jacob Perrin, and joining me will be Marco Spilker. We're in the Autonomous Driving and Software Engineering Group at dSPACE Inc. in Wixom, Michigan. And the topic of today's Learning Connection will be simultaneous in-vehicle sensor data logging and ECU prototyping. So we talk about sensors. What types of sensors are we talking about? What types of sensors are on an autonomous vehicle? The first sensor type is going to be your cameras. These are going to be around the vehicle in addition to your radars, LiDARs, and occasionally ultrasonics. What types of buses do each one of these sensor types use? Well, we might have a CAN or CAN FD bus, or maybe a few, maybe something like 8. These CAN FD buses are going to be what's used for your radars and sometimes cameras that output object detection lists. In addition, we'll have various Ethernet networks, which are becoming more and more common, both standard Ethernet and automotive Ethernet. And these are going to be for your radars and LiDARs, and occasionally if you have some sort of giggy vision camera. And lastly, we'll have our serializer, deserializer, I/O types. These are going to be your GMSL, FPD-Links, MIPI A-PHYs, and traditionally, at least, these are used for cameras, though we have seen some radars also using this I/O type. So the other word that's important in the title of the Learning Connection is simultaneous. And by simultaneous, we mean this concept that you'll hear me say over and over in this webinar, TAP. So what do I mean when I say TAP? Well, like any good fifth grader, we can reference Wikipedia. So Wikipedia has to say that a network tap is a system that monitors events on a local network. A tap is typically a dedicated hardware device which provides a way to access the data flowing across the computer network. So something like Watergate, if you will. And so the different sensors that are going to be connected are the same. You have your camera, radar, and LiDAR. This tap hardware is going to sit in between those sensors and your ECU hardware. Why would we want to do tap? Why will we want to sit some device between our sensors and our processing system? The first reason that we might want to do that is because the sensors may not function correctly unless we have the ECU available. An example of something like this is when we have an ISP, an image signal processor, inside the ECU. That image signal processor might be necessary in order to get the correct sensor data, in order to get the correct white balance, what have you, on the camera side. Then you might wonder why not just record directly on the ECU? The reason for that is that it may not be possible to add a large-scale storage, maybe an SSD or some network SSD to the ECU. You may not have the ports available. It may not just make sense. Even if you do have the ability to add it physically, you may not want to add the computational overhead of actually pushing the data from the file system to disk. And with that, even if we wanted to do that, it's not necessarily going to be representative of our production environment. So we probably aren't going to be doing this large-scale data logging in a production environment. And so in order to do our on-road testing in as close high fidelity to a production environment as possible, we may not necessarily want to hook up the storage directly to the ECU. Another reason we may want to do this in-vehicle sensor tap is that not logging sensor data during our on-road testing is really just wasting the data. If you were to simply not have a logger at all and connect the sensors up to the ECU and do your on-road test, then any data that you might have been able to collect, any data about any failures of the system, you're just going to throw out, and that won't be useful for your validation activities later. And the final reason we might want to do in-vehicle sensor tap is going to be because we can actually do more intelligent data logging by connecting the ECU. We might be able to use something like a confidence threshold or some failure conditions on the ECU to actually trigger data logging, so that we're not logging all the time, but only logging when we have some sensor data that's particularly interesting. Now, talking more about each of the different I/O types and how we will go about tapping each particular one, starting with the Canbus. So tap for Canbus is really quite easy. Because it is a bus, all of the data is already available to each of the nodes of that bus, meaning that we have a passive tap that's inherent and no need to add any additional hardware for some active tap interface. We can just connect the logger to the Canbus and log the data directly. Ethernet is a little bit more complex. For Ethernet, we need to have some additional hardware. We can't just have one interface to connect to the network. We need to actually pass the data through that interface. This is accomplished via an internal network bridge, but it does require 2 ports for each one network that you're trying to log. And this is going to be possible for both standard Ethernet and automotive. Lastly, we can talk about these serializer, deserializer interfaces, these raw camera interfaces. And this is really quite difficult. This requires both deserialization and reserialization at the logger, where we connect the serializer of the camera to a deserializer on the logging system. We then reserialize the data through the FPGA as quick as possible back out into the ECU hardware with as minimal latency as possible, typically on the microsecond level. And this is not only difficult because we have to have all of these different matching deserializers and serializers, but the software configuration is really important, and it's different between each SerDes type, as well as how each particular customer uses that serializer, deserializer, and the register settings that they have and the different features that they turn on. Similar to Ethernet, you're going to have one deserializer and one serializer for each camera interface that you're attempting to tap, meaning that you need 2 times the amount of interfaces that you have sensors. Now, talking about the dSPACE solution, the dSPACE hardware that will allow us to do this logging and tapping, that's going to be the AUTERA AutoBox. And this is going to be a Linux server in a vehicle. Not just some industrial PC, though. It's really a ruggedized, purpose-built computer for the purposes of this data logging activity. So it's robust. It comes from the same product development teams that created our micro AutoBox, been used for decades. It's going to be shock and vibration proof and available for DC power from the vehicle, etc. Speaking of computation, it's going to be this server motherboard, this 12-core Intel Xeon, that's going to allow us to do all of this tapping and logging with the performance required to actually get all the data to the SSD. We can have up to 256 gigabytes of RAM, and we can add a GPU for doing some sort of more intelligent data logging using some neural networks. And then to actually connect to the different I/O types, to connect to your CAN, Ethernet, GMSL, FPD-Link, we have these 6 PCIe slots available in these 2 cages, and we'll add some PCIe cards to these 6 slots, which will allow us to connect to the different I/O of our sensors, according to our particular sensor set. So what do each one of these cards look like? So starting from left to right, we have the DS7342 or 43, and that's going to be our CAN-FD card. That's going to have 8 channels, and that's going to therefore allow us to connect up to 8 different CAN buses and get the data and log the data, in addition to the ECU being able to access that data on the bus. Next card is going to be our DS7333 or 35. Ethernet card, and this is a PCIe card with 2 daughter boards for either standard Ethernet or automotive Ethernet. It has 4 effective controllers for connecting to either the sensors or the ECU. And in a tap mode, then we're going to be able to tap up to 2 Ethernet networks per slot per Ethernet card. Lastly, we have the AUTERA PCIe grabber, and this is going to be an 8-channel, 8-connector FACRA Z connecting up to our serializer deserializer interfaces. And then this is therefore going to allow us to tap up to 4 different camera interfaces with alternating deserializers and serializers. So you might wonder, why do this all in one box? Why have a system where we're simply connecting the cameras, the logger to the ECU, and not using some external tap boxes? Well, the reason for this is because it reduces a few things, starting with time synchronization complexity. You'll need to add a GPTP network between the tap devices and your logger if you'd like to do some sort of decentralized logging and set up a full master-slave mechanism there. In addition to having that GPTP and potentially also a separate line for the actual data, you'll actually need power, and all that's going to add some additional wiring complexity. Even if it's not necessarily a lot of weight, it's still complex, and you have to figure out how to get all the wires rigged to the AUTERA system. I said that one of those wires is power. Power is going to be one thing that each one of these tap devices is going to require. And so doing it all in one unit will reduce the power requirements. And because each one of these are separate devices, they require space, which means that if we're doing this sort of centralized data logging approach, that's going to reduce the in-vehicle footprint. However, there may be some cases where you'd like to do a more distributed logging architecture, where you'd like to have external tap devices in addition to having just a logger here. Maybe because you ran out of PCIe slots in the logging system, you need more Ethernet or you need more camera interfaces. And so if you'd like to do that, that is something that we can support with the new sensor data interface, the new SDI box. This SDI box is today supports these camera interfaces, these GMSL and FPD-Link interfaces, and we can connect those cameras to the SDI. The SDI will then propagate the data to the ECU, in addition to popping out the data from the Ethernet channel here to the AUTERA logger using the ASAM CMP, the capture module protocol that was recently released, and everything will be time synchronized over the GPTP. So in summary, the AUTERA is a complete data logging solution to connect to each one of your sensor interfaces, your cameras, radars, and LiDARs. If we're doing something like a tap and not just simply logging the data, we also need to be able to propagate that data to the ECU with minimal latency and without any interruption or disturbance of the data itself, as well as log the data to our SSDs with up to 50 gigabits per second of data logging bandwidth. And now I'll pass it over to Marco, our resident camera engineering expert, who will show the AUTERA doing tap in action.
Thank you, Jacob. My name is Marco Spilker, and I'm here as a resident camera engineering expert here at dSPACE Inc. Today, I will show you the tap functionality of the AUTERA system with the real ECU, which is in our case a PX2 from NVIDIA. We are feeding the real-life camera from one of our Seconix cameras here to the system and passing it through to the PX2. To demonstrate that the ECU is fully under control over the camera connection, I can sever the connection between the ECU and the camera, and we will see that both camera streams are stopped. even though the camera is connected to the AUTERA, which means that the trigger signal, which is sent by the ECU, doesn't reach the camera anymore and was particularly feed through the AUTERA system to the camera. If I reconnect now the ECU to the camera, the trigger signal will come back through the AUTERA system to the camera, and the feed is alive again. This means that the AUTERA system is only here now as a pure logger, but it doesn't have to be as dumb. With the help of the GPU in the system, we can run AI algorithms to detect certain features in the camera feed and just be smart about our logging. So we don't fully saturate our SSD and can much longer on the road. This concludes our demo of the AUTERA system with this tech functionality. And I thank you for your time and listening. And we're heading now for a Q&A session.
dSPACE, your partner in simulation and validation.